Go to TAPgiles.com to learn dreams, engage my services, and support the channel. So if we have this position and we wire it into the first operand, and we have another position and we wire that into the second operand, and we put this into distance between vectors mode, then this sends out the distance between those two positions, those two vectors. So if we wire it in here, we can see it's 3.43 distance, and if we move them closer, it gets smaller, further away, it gets bigger, and even if it's like going left instead of right, it doesn't matter. The order these go in are plugged in to the calculator. It will just be the distance between those 2 points. And then there's vector length. So we talked about this is just giving us a position vector, and the length of that vector is from the 0 point in the scene, the distance going to that position. So that's what this is sending, the vector length, and it's sending out 4.48. And the interesting thing is these wires, so this is a fat wire, and as we saw a bit earlier, because this is a 3D vector, we have these three numbers. When we split it, and it's a 3-number type of fat wire, but even that has the distance in it, and known as the magnitude or the length. These are just different terms for the same thing. And so if we remove that and just wire that in, it actually gives us the same answer. And you can actually see the that default value of the distance, the length of that vector, being shown in the calculator there. Then we have Normalise vector. So remember we talked about this has a distance from 0, and that's the vector's length. And when it's normalized, it only has a length of 1, but points in the same direction. That's what this does. It normalizes this vector. And then the output, if we put that into a splitter, we could see the individual parts of it. So let's get two splitters actually. So let's wire that into the position. So this is the position. This is the normalized vector version of the same position. So if it was pointing straight up, it would be basically just 1 going in the Y direction. These always say A, B, and C because it's just general purpose. There are 3 numbers, let's label them A, B, and C. But in this case, we're talking about things in the scene, so the order is X, Y, and Z. So when it's going straight up from the origin, the normalized version is just 1 in the Y, and if it was straight across, it would be 1 in the X, and they're a bit off because I'm not like being exact and stuff. And you can see it's kind of similar over here. The Y, the X is the biggest value compared to the other two, but over here everything's just scaled down because it's actually the way you calculate this kind of stuff is you figure out the length of the length of the vector. So this is like 5. And then you just divide it by 5, so then it shrinks it down, as we saw earlier with the arrow, until it's only 1 length. It's only 1 long. And if it was like tiny like that, you could see these numbers are really small, and so its length would be very small. But then it boosts it up so that it becomes 1 again, but going in the same direction. So if you like position these carefully, you can get to about the same numbers, and that means that's about 1 from the origin, and that's what normalization does. The reason you'd want normalization is if you had an object here and you had the location here and you want it to point towards it, one way would be to use a lookout rotator and then give it the normalized location of this, because it would give it the direction of where this is. For example, but also these other things, they kind of need normalized vectors to work properly in some cases. I'm going to skip those two for now and go on to angle between vectors. Angle between vectors means if you got the origin there and it's got a vector, we got a vector to here, That's what this is representing. And then we've got a vector to here, and wire that in there. It kind of figures out the angle to this one, and the angle to this one, and the kind of distance between them. So if we add a line there, and a line there, then we'd want the angle here, and that's what it's outputting. So, but interestingly, with this particular operation, it sends us degrees instead of radians. So this is 45 degrees. If you put that around to there, you'll expect it to be 90 degrees because it's kind of a quarter around, and it's giving us about 90 there. All of that is measured from this center point of 0. But what if we had these kind of over here, and we had a third point there, and we wanted to measure from here, so that angled round to there would be 90 still. Let's give this a different color. So we want to kind of offset this whole thing so that it goes down to the origin again, and then it would give us the 90. And as we were talking about earlier, though, with the arrows, if we subtract one vector from another, we're kind of moving it backwards along that vector. So if I again draw out what these vectors look like, you've got one to there. We want to kind of subtract from those so that that moves to there and that moves to there. So we just subtract that as we just said. So let's get a calculator and subtract, and then we take that and subtract this like origin point from it. And we do the same for the other vector over here, and subtract the new origin. And then we do the angle between vectors for that, and that gives us 90. And now if we like move it around here, we can see we're getting what we might expect. We've got like 45 degrees, we've got 180 degrees, 90 degrees, even though they're not around the origin down there. And if we move this, the angles will change as well. So over here now it's 180 degrees. Over here it's 90 degrees again. We move over here, we're getting like a 45 degrees thing going on, and stuff like that. Thanks for watching. I hope you learned something interesting. Go to patreon.com/TAPgiles to learn something new every day.